Imagine a calm evening in a sprawling city. Glass towers glow with warm lights, traffic hums below, and everything feels solid, stable, and predictable. Now picture that same skyline, with a single impossible change, an enormous circle of empty space where a towering building stood just moments before. No explosion, no fire, just a silent void where the ground opened without warning. It feels like a scene from a big-budget disaster film, but the unsettling question is whether nature could really pull this off. The idea of a skyscraper vanishing into the earth overnight sounds absurd, but the truth is that our planet's surface is not as still as it seems. Beneath city streets, offices, and subway lines, geological processes are constantly reshaping the ground, sometimes quietly and sometimes violently. To understand whether this nightmare scenario could ever be real, we have to start with how the Earth creates sinkholes in the first place. A sinkhole is a natural depression or sudden collapse of the ground surface, and it forms when underground material is removed or destabilized. These collapses don't strike randomly, they occur most often in what geologists call karst regions, areas where the underlying bedrock, often limestone, dolomite, or gypsum, dissolves gradually in water. When rainwater absorbs carbon dioxide from the atmosphere, it becomes slightly acidic. Over long periods, that weak acid seeps into the ground and begins dissolving the rock below. While this chemical reaction is extremely slow, it steadily hollows out passages, chambers, and networks of underground voids. On the surface, the landscape may look perfectly normal, even though deep beneath it, empty spaces are quietly growing. There are two main ways these hollow spaces reveal themselves. Sometimes the surface slowly sinks as underground cavities expand, creating gentle depressions. More dramatically, a sudden collapse can occur when the roof of an underground void becomes too thin to support the weight above it. This is what geologists refer to as a cover collapse sinkhole. These collapses can happen quickly, sometimes within hours, and the result can be a steep, circular hole that appears with frightening speed. Even more troubling, human activity can make these collapses more likely. Excessive groundwater pumping, leaking drainage pipes, poorly managed stormwater systems, and construction vibrations can destabilize the upper layers of soil and accelerate the natural process. Around the world, sinkholes have swallowed cars, roads, and homes in a matter of minutes. In some cities, they have consumed entire sections of streets. These events remind us that the Earth's surface is not a solid shell, but a thin layer resting on top of dynamic, dissolving rock. Still, while the destructive power of sinkholes is undeniable, the question remains, could any of these natural processes possibly scale up to something large enough to take down a modern skyscraper? Next, we will look at what it actually takes to hold a skyscraper upright, and what conditions would be required for the ground below one to collapse completely. To understand whether a sinkhole could ever take down a skyscraper, we need to look beneath the surface, literally. A modern high-rise may appear delicate from a distance, all shimmering glass and narrow lines, but everything about its design is built around one goal: making sure it stays firmly attached to the earth. The height you see above ground is only part of the story. The real strength of a skyscraper lies in what anchors it deep below street level. Engineers spend years studying the geology of a building site because a tall structure cannot rely on surface soil alone. That loose upper layer shifts with moisture, compacts under weight, and is far too unstable to support hundreds of thousands of tons of steel and concrete. Before construction even begins, engineers conduct detailed geotechnical investigations to understand every layer beneath the future tower. They drill deep boreholes to extract core samples and use seismic testing to map underground conditions. These studies reveal whether strong bedrock is close to the surface or buried far below. In cities built on exceptionally tough rock, like the schist beneath Manhattan, skyscrapers can anchor directly into the solid formation. This natural foundation allows engineers to transfer the immense weight of the building into rock that has been stable for millions of years. In places where strong bedrock lies deeper, engineers rely on deep foundation systems. One common method uses piles, long columns made of concrete or steel, driven far into the ground until they reach a layer capable of supporting massive loads. Some of the world's tallest buildings sit on foundation piles that extend tens of meters below the surface. These piles do not depend on loose soil to hold them in place. Instead, they carry the building's weight downward until it reaches firm, compressed ground or bedrock. This creates a foundation system that behaves like an array of incredibly strong legs supporting the structure. Many skyscrapers also include massive reinforced concrete mats at their base. These mats spread the building's weight more evenly and improve stability in areas where soil layers vary in strength. Combined with deep piles or caissons, these mats help ensure that no single weak layer can undermine the entire structure. Builders also design foundations with safety factors well beyond the building's normal load to ensure that seasonal changes, groundwater fluctuations, or minor soil shifts cannot compromise the structure. Because of this complex engineering, a skyscraper is not simply resting on the earth, it is locked into it. For a sinkhole to threaten a building of this scale, the collapse would need to be far larger and deeper than anything typically seen in urban environments. It would have to destroy not only the surface layers, but also the stable material deep below that the foundation depends on. In the next part, we will examine what kind of extreme conditions would be required for such a collapse to unfold. A major contributor is the slow decay of underground infrastructure. Old water mains, storm drains, and sewer lines can leak for years, washing away soil grain by grain. In large cities, some pipes are more than 100 years old, and even minor cracks can create steady erosion cavities that expand unnoticed. Engineers call this process piping, and it can hollow out huge underground voids long before surface cracks ever appear. Another issue comes from the weight of the city itself. Skyscrapers, elevated highways, subway tunnels, and heavy traffic all put enormous pressure on the ground. If the soil beneath is already weakened by natural dissolution or quiet water flow, that pressure can accelerate subsurface collapse. Even well-designed foundations can become stressed when the geology changes unexpectedly. Construction activity also plays a role. Deep excavation for basements, parking garages, and utility tunnels can alter groundwater levels. When groundwater drops, the support it once provided to the soil disappears. In regions with soluble rock, losing that water balance allows underground cavities to grow faster. In other cases, vibrations from construction equipment can destabilize loose or water-softened soil, encouraging the ground to shift. Modern cities often hide their geological past. A skyscraper might be built over an old filled-in quarry, an abandoned drainage channel, or soil that was artificially compacted decades earlier. These materials can behave unpredictably over long periods of time. What looks stable at the surface may not reflect what is happening deep below. Climate shifts add another layer of risk. Periods of heavy rainfall can overwhelm drainage systems, increasing the water pressure underground. When too much water moves through fractured rock or loose fill, it can trigger sudden subsurface erosion. Meanwhile, long dry spells can shrink certain soils, especially clay-rich layers, creating gaps around foundations that weaken surface support. All of these factors combine to create a complex and often invisible threat. Cities rarely fail from a single cause. Sinkhole disasters usually happen when multiple small vulnerabilities line up at the worst possible moment. And because most of the danger is hidden beneath pavement and concrete, early warning signs are easy to miss. Modern sinkhole detection begins with ground-penetrating radar. This technology sends radio waves into the earth and measures how they bounce back. When engineers see irregular reflections, it can indicate underground voids, weakened soil, or pockets of dissolved rock. Ground-penetrating radar is especially useful in urban environments because it can scan paved surfaces without excavation. Another essential tool is microgravity surveying. The concept is simple. Empty spaces underground have slightly lower gravitational pull than solid ground. When sensors detect subtle gravity changes, analysts can map where underground cavities might be forming. This method is valuable for locating voids beneath foundations, roadways, and utility corridors. LiDAR scanning is also becoming more common in cities. By bouncing laser pulses off the ground from aircraft or drones, LiDAR can detect even tiny changes in elevation. If a surface begins to sag by a fraction of an inch, it may signal that the soil below is shifting or settling unevenly. These early depressions often develop long before a sinkhole becomes visible. Acoustic monitoring adds another layer of protection. Sensitive instruments can pick up faint cracking, shifting, or moving soil beneath structures. Changes in natural underground vibrations, known as seismic noise, help engineers identify when the ground is loosening or collapsing internally. This approach works continuously, providing early warnings without interrupting city activity. Soil sampling also plays an important role. Engineers drill narrow boreholes to study the density, moisture content, and mineral composition of the ground. In regions with limestone, gypsum, or salt deposits, these samples reveal whether dissolution or water infiltration is increasing. In urban areas, sampling helps verify whether old fill material is compacting or breaking down with age. Some cities use groundwater monitoring wells to watch for sudden water level changes. A rising water table can force soil apart, while a rapidly dropping one can remove essential buoyancy that supports underground cavities. These shifts often occur weeks or months before ground failure becomes visible at the surface. Remote sensing satellites add long-range oversight. Using a technique called interferometric synthetic aperture radar, satellites can track millimeter-level land movement over time. When the ground begins to sink slowly, even at a pace too small for a person to notice, these measurements provide critical warning signs. By combining all these technologies, engineers create a layered defense system. No single method is perfect, but together they dramatically improve the chances of identifying dangerous subsurface changes before a sudden collapse occurs. The idea of a skyscraper disappearing into the earth in a single night is dramatic, but the physics behind these structures makes that outcome extremely unlikely. Modern high-rise buildings are anchored by deep foundation systems, such as drilled shafts and reinforced concrete piles that extend many stories into stable ground layers. These foundations distribute weight across multiple contact points, meaning a failure at one location rarely causes the entire building to fall suddenly. Documented large sinkholes, including those in regions with active karst terrain, typically develop in stages. The collapse often begins with a subterranean cavity that enlarges gradually as water dissolves underlying rock. Even when a final collapse is abrupt, the surface usually shows early warning signs such as cracking pavement, tilted utility poles, and localized subsidence. Skyscrapers with active monitoring systems would detect these shifts long before catastrophic failure. For a high-rise to fall into a sinkhole in a single night, an extreme set of conditions would need to occur simultaneously. The ground would have to contain a massive hidden void directly beneath the building. The supporting bedrock would need to fail without warning, and the building's foundations would need to lose structural support at nearly every anchor point at once. There are no recorded cases of all these factors aligning beneath a modern skyscraper. More realistically, partial foundation loss could cause structural distress rather than sudden disappearance. A building might lean, fracture, or experience settlement that forces evacuation, but engineers could reinforce or stabilize the site before complete collapse occurred. In urban settings, rapid emergency response and ground stabilization protocols reduce the likelihood of uncontrolled failure. If a worst-case sinkhole opened under part of a skyscraper, the collapse would be uneven. One section might drop while the rest remained intact, creating a visible tilt or break rather than a clean vertical plunge. Rescue agencies would intervene immediately, and structural engineers would assess whether the remaining portions could be stabilized or required demolition. While overnight total collapse remains highly improbable, smaller sinkholes near skyscrapers can still cause serious damage. Roads, sidewalks, and nearby low-rise buildings are more vulnerable because they rely on shallower foundations. Many cities monitor past subsidence zones to prevent development on unstable terrain. The real risk lies not in skyscrapers being swallowed whole, but in the gradual weakening of urban ground caused by leaks, aging infrastructure, and changing water tables. Continuous monitoring, routine inspections, and strict geological surveys remain the most reliable way to prevent disaster.